So this lecture carries on looking at organic chemistry. So what we're hoping to do is define and identify the different types of structural isomers, define the term stereoisomerism, and identify cases of what we call EZ isomerism. And then we want to look at using Korn-Ingold preload priority rules to classify E and Z isomers. So to start with the yellow box definition, isomers, these are molecules that have the same molecular formula but a different chemical structure. So they'll have the same number of each type of atom, but they're arranged differently, bonded differently, or differently in space. There are two main types of isomerism that we've got to become familiar with. They are structural isomerism and stereoisomerism. So structural isomers, these are molecules that have the same molecular formula, but a different structural formula. So all the atoms are bonded differently, so they're bonded to different atoms in a different way, but you've still got the same number of each type of atom. For example, if you look at butane and 2-methylpropane, if you add up the number of carbons, it's 4, and if you add up the number of hydrogens, it's 10 in both cases. However, how they're bonded together is different. So 2-methylpropane has obviously got that carbon branch, where butane is just a straight carbon chain. So they are structural isomers of each other. They've got the same molecular formula, but a different structural formula. There are three different types of structural isomers. We've got branch chain isomers, position isomers, and functional group isomers. So let's look at each in turn. So firstly, chain isomers. These have the same functional groups, but different arrangements of the carbon skeleton. So for example, you've got pentane there. Two branch chain isomers of pentane would be methylbutane and dimethylpropane. So each of those has got 5 carbons and it's got 12 hydrogens, but they've got a different number of branches in each case. So pentane has none, methylbutane has 1 methyl branch, and dimethylpropane has obviously 2 methyl branches. So same number of carbons, same number of hydrogens, but they're just bonded differently. One's got more branches, but those two have got more branches than the other. In position isomers, you've got the same carbon skeleton and functional group, but the functional group is in a different place. So for example, if we look at butanol, we've got butan-1-ol on the left there. We could alternatively have butan-2-ol. So again, if you add up the number of each atom, they'll be exactly the same. The functional group is the same. It's just the position of the functional group that changes. So obviously in butan-1-ol, the OH is on carbon 1, and butan-2-ol, we've just moved the OH to carbon 2. So they are position isomers. If we look at this one here that we've got in blue, I'm hoping you'll spot that that is actually still butan-2-ol. So that is not an isomer of butan-2-ol. It is butan-2-ol. So you've got to be careful of just moving the OH around when it could be that you join two molecules that with different numbering of carbon will be the same. So in each of the pairs of molecules below, identify the type of structural isomerism. So just have a couple of seconds to think about that. So hopefully in the top one, you can see that they are branch chain isomers. So you've got hexane and methylpentane. Obviously, methylpentane has one more branch than hexane, which has none. In the middle pair, you've got methylpentane in both cases. All that happens is the methyl moves position. So they are position isomers. You've got 2-methylpentane and 3-methylpentane. At the bottom there, both of those are dimethylbutane. But one is 2,3-dimethylbutane and the other is 2,2-dimethylbutane. So they are again position isomers, same number of branches, you've just moved them. So branch chain for the top ones, position isomers for both of the bottom pairs. The final type was functional group isomers. These have the same molecular formula, but they contain different functional groups. So one classic example is cycloalkanes and alkenes. So if you look at cyclohexane there and hexene, they've got the same number of carbons, same number of hydrogens, but a different functional group. The one on the left doesn't really have one. The one on the right has the carbon-carbon double bond as its functional group. So same number of each type of atom, but a different functional group. They are functional group isomers. Another classic example, the aldehydes and ketones. So propanal and propanone, same number of each type of atom, but one is an aldehyde and one is a ketone. So same number of type of atoms, but different functional groups. So we can define and identify the different types of structural isomers. We now need to move on to look at stereoisomers and identify cases of EZ. So in stereoisomers, these are compounds with the same structural formula but a different arrangement of the atoms in space. So that means that the atoms are all bonded to the same atoms they were before, but for some reason they're held differently in space. And there are two types of stereoisomerism. We've got EZ and we've got optical, which we will look at next year. For now, we just want to focus on EZ. So EZ isomerism occurs in alkenes, and a molecule must satisfy two criteria in order for them to show EZ isomerism. The first is they must have a carbon-carbon double bond, hence why it happens in alkenes. The second criteria is that each carbon of that double bond must have two different groups attached to it. It can't have, for example, two hydrogens. You just won't get EZ isomerism if one of your carbons of the double bond has two hydrogens on it, because they're not two different groups. So they're the two things you need. One classic example is butene. So these are the two isomers, two stereoisomers of butene. So on the left-hand side there, you can see you've got your carbon-carbon double bond. The carbon on the left has a CH3 on it and a hydrogen on it. And the carbon on the right of the double bond has a CH3 and a H on it. So each of those two carbons has two different groups on it, a CH3 and a H. So they fulfilled both criteria. They've got a double bond, and each carbon of the double bond has two different groups on it. Now that double bond does not rotate. There is no rotation about a double bond. That means that wherever those CH3s are, they are held there. They could be at the top or they could be at the bottom, and you can't switch them because you can't rotate around the double bond. And have a look at these 5 molecules. You need to decide which can exhibit EZ isomerism. Okay, so hopefully you've spotted this first one can. Each carbon of the double bond has two different groups. Each has a chlorine and a hydrogen, so that one can. This one also can, the top right one. Each, again, you've got a double bond, and each carbon of the double bond has two different groups attached. This one down here cannot. So the left-hand carbon of the double bond has two hydrogens on it, so they're obviously the same. So this one does not fulfill the second requirement. This molecule here, this one will. So each carbon of the double bond has a CH2, CH3 on it, an ethyl group, and also a hydrogen. So that one will show EZ isomerism. This bottom one here, hopefully you've spotted, will not be able to because it doesn't even have a double bond. So that will definitely not exhibit EZ isomerism. So we can define and identify different types of structural isomers. We can also now define the term stereoisomerism and identify cases of EZ isomerism. The final thing we need to do is use Cahn-Ingold-Prelog priority rules to classify E and Z isomers. So let's start by looking at butene. So we have to assign one of them to be the E isomer and one of them to be the Z isomer. And to do this, we use the Cahn-Ingold-Prelog, the CIP priority rules. So in order to assign priorities to the two groups on that carbon, you have to decide which one has the highest atomic number, and that one is given the priority of 1. The other one has the lower priority of 2. So if we look at butene on the left-hand side there, each carbon has a CH3 and a H, and hopefully you'll spot that CH3 has the highest atomic sort of mass there. You've got a carbon and 3 hydrogens, so the total mass of that group is 15, whereas the total mass of the hydrogen group is just 1. So in each carbon, it's the methyl groups that is the high priority group. And obviously it's the same for the other side. So on the left-hand side, your two highest priority groups are on the same side of the double bond. So that is called the Z isomer. On the right-hand side, you can see the two highest priority groups are on opposite sides. So what is shown there is the E isomer. In order to denote this in the name, we literally put an italic Z or E at the start of the name. So the left-hand isomer there is Z-butene, and the right-hand isomer is E-butene. Another example then, we've got dichloroethene. So each carbon has a hydrogen and a chlorine, and you should be able to spot that obviously the chlorine has got the highest atomic mass. So in each case, it's the chlorines that are the highest priority. So in your left-hand isomer there, your two highest priorities are on the same side. So that's the Z isomer. On the right-hand side there, you've got the two highest priority groups on opposite sides of the double bond. So that is the E isomer. So that is Z12-dichloroethene, and this is E12-dichloroethene. So pause and have a go and tell me what isomers we have here. Are these E or are they Z? Okay, so that first one you should see is Z. So the two highest priority groups are the chlorines and they're on the same side. So that is the Z isomer. The middle one here is a little bit harder to see, but if you look at the double bond with your head sort of tilted to the left a little bit, you can see the two ethyl groups are on opposite sides of the double bond. So that is the E isomer. On this end one, on the left-hand carbon, the highest priority group is the chlorine. On the right-hand carbon, the highest priority group is the CH3, and they are on the same side. So that is the Z isomer. So we can define and identify the different types of structural isomerisms. We've got branch chain, we've got position, and we've got functional group isomers. We then know what the term stereoisomerism means, and we've looked in detail at EZ isomerism. We can identify cases of it, and we can use the Kahn-Ingold preload priority rules to classify isomers as E or Z.